Enums and pattern matching. In this chapter, we'll look at enumerations, also referred to as enums. Enums allow you to define a type by enumerating its possible values. First, we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching in the match expression makes it easy to run different code for different values of an enum. Finally, we'll cover how the if-let construct is another convenient and concise idiom available to you to handle enums in your code. Enums are a feature in many languages, but their capabilities differ in each language. Rust's enums are most similar to algebraic data types in functional languages such as F#, I prefer to call it G-flat, OCaml, and Haskell. Defining an enum. Let's look at a situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, there are two major standards, version 4 and version 6. These are the only possibilities for an IP address that our program will come across, so we can enumerate all possible values, and that's where enumeration gets its name. Any IP address can be either a version 4 or a version 6, but not both at the same time. That property of IP addresses makes the enum data structure appropriate because enum values can only be one of the variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in our code by defining an IP attr kind enumeration and listing the possible kinds an IP address can be, version 4 and version 6. These are known as the variants of the enum. So we have our first enum, calling it IP attr kind, v4, v6. IP attr kind is now a custom data type that we can use elsewhere in our code. Enum values. We can create instances of each of the two variants of IP attr kind like this. Let 4 equal IP attr kind : version 4. Let 6 equal IP attr kind : version 6. Note that the variants of the enum are namespaced under its identifier, and we use a double colon to separate the two. The reason this is useful is that now both values, IP attr kind version 4 and version 6, are of the same type. We can then, for instance, define a function that takes any IP attr kind. So we have a function called route, and it takes an instance of IP attr kind. We can call this function with either variant. So calling route with version 4 or version 6 should work. Using enums has even more advantages. Thinking more about our IP address type. At the moment, we don't have a way to store the actual IP address data. We only know what kind it is. Given that you just learned about structs in Chapter 5, you might tackle this problem as shown in listing 6.1. So here I have enum in a struct. Wait, is that what I did? Yeah, the second way. Yeah, okay. So we've got our enum, and then a struct, IP attr. And over here I've called it IPAtterStruct so I don't get confused. And the struct has two fields. It has a kind field, which must be of a type IPAtterKind. It can be 4 or 6. And then we have an address field, and that is a string. So here we have the second way. So we can let home equal an IPAtterStruct with a kind, IPAtterKind version 4, and address string from 127001, and then let loopback equal an instance of an IPAtterStruct. The kind is IPAtterKind version 6, and the address is string from 1. Here we've defined a struct, IPAtter, that has two fields. A kind field that is of type IPAtterKind, the enum we defined previously, and an address field of type string. We have two instances of this struct. The first, home, has the value IPAtterKind version 4 as its kind, with associated address data of 127001. The instance loopback has the other variant of IPAtterKind as its kind value, version 6, and has address : 1 associated with it. We've used a struct to bundle the kind and address values together, so now the variant is associated with the value. We can represent the same concept in a more concise way using just an enum, rather than an enum inside a struct, by putting data directly into each enum variant. This new definition of the IPAtter enum says that both version 4 and version 6 variants will have associated string values. So here I've got it more concise. So now we have the enum is just IPAtter, or I've called it IPAtter enum, and it's got the two variants, version 4 and version 6, and each of them has this associated data in the form of in the type string. So we can say function the third way, let home equal IPAtter version 4, and then I'm a little unsure what to call this. It looks like a function argument syntax, or so this would be a parameter syntax, and then this would be an argument syntax. I don't know what I've seen this, the two parentheses together, as an empty tuple. So I've sort of thought of, anything that's not, well, okay, so that's not a tuple, that's a string. I was going to say, can I just call this, if this is the empty tuple, then can I say this is a tuple? But no, I can't, because it's a string. Anyway, I want to know what to call this, and whether it's a, it is a parameter. It might not be defined as that, but it just, it's a parameter, yeah. Not, you know what I'm trying to say. And then I guess we would call this is sort of a type of argument. Anyway, so here we've got let loopback equal an instance of the IPAtter enum version 6, and it has to take a string, and so we're going to give it a string from : 1 from this string slice. We attach data to each variant of the enum directly, so there's no need for an extra struct. There's another advantage to using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 type IP addresses will always have 4 numeric components that will have values between 0 and 255. If we wanted to store version 4 addresses as 4 U8 values, but still express version 6 addresses as 1 string value, we wouldn't be able to do that with a struct. Enums handle this case with ease. So here I've got different types and amounts of data, and my enum is called IPAdder enum with types. I mean, really, if I'm going to be specific, I should say with different types, because the other one had types too. No, the other one had a type. Ha! Okay, so we've got version 4 has data attached to it in the form of what appears to be a tuple, because it is a tuple of U8s, and then version 6 still has the string. And then we could we're calling the function? No, so this is just because I need a scope to. What I really needed was these things, right? But anyway, let home equal IPAdder enum with types version 4, and it's going to take these 4 U8s. What was floating? Yeah, version 4 U8 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 U8. I did eat. So we've got that, and then let loopback equal IPAdder enum with types version 6, and it still wants a string, so we give it 1. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. As it turns out, wanting to store IP addresses and encode which kind they are is a thing. So the standard library has a definition we can just use. So the way the standard library defines IPAdder, it has the exact enum and variants that we've defined and used, but it embeds the address data inside the variants in the form of 2 different structs, which are defined differently for each variant. So, do I have this? No, I didn't put this. Did I? I don't know. I did not. Okay, so in the standard library, there is an enum called IPAdder, and it has version 4 and version 6, and it has the same so the data type that it takes for as a parameter of version 4 is the struct IPv4 adder, and of course they didn't show us what's in it, but I presume it's, well, we can assume that the version 4 adder struct has this, right? I mean, it'll probably take a tuple of. Should I click on this? Okay, I did it. Variants, methods. I want that to go away. You're taking up my space. So here's our structs, and then what do they look like? Show declaration. I'm not real comfortable with navigating this documentation yet. It's hard for me to focus on focus with my eyeballs. So that's the reason I'm doing this is because I want to be able to hear the book. And I guess it helps me to read it. One thing I've noticed though is that when I go back and listen to these videos that I'm making, my voice lulls me straight to sleep. And that's not exactly what I was going for. Maybe I should interject startling noises or change the change the, yeah, change it to light. Ah, my eyeballs. All right. Yeah, okay, so, right, so whereas the idea that they gave us, that they sort of drew out of us, saying, hey, don't you want to use what you just learned in Chapter 5? That would be to put the enum inside of a struct, where we have the kind field, or the IP-adder kind, as its, but see it in the, with a struct, we're naming the field, and then we are specifying the type that the field accepts as a value. And then the syntax is different for enums, because in the enum we have, instead of a scope block, which, or instead of a whatever we call these things, we've got this. Maybe that's why they introduced it sort of the way they did, because this is starting to be a little bit conflated, or conflating the syntax, I mean. But the example they fished out of us was to put the enum in the struct, and then they said, okay, well, actually you can just do it with an enum and associated data. And then they said, well, okay, but here's the way we did it. We did an enum with associated data, and then the data we associated comes from two different structs. This code illustrates that you can put any kind of data inside an enum variant: strings, numeric types, or structs, for example. You can even, get this, you can even include another enum. Let that sink in. Nested enums. Also, standard library types. Here's another thing. Standard library types are often not much more complicated than what you might come up with. You know, you're good at this. You can do it. Note that even though the standard library contains a definition for IP-adder, that did not stop us from making another one. And there's no conflict because we did not bring the standard library's definition into our scope. We'll talk about that in Chapter 7. So how would we get it into scope? I'm doing it. I'm clicking on it. Why did I click on it? Oh, here we are. So we would have to say, use standard net IP-adder. Yes. We didn't. Let's look at another example of an enum in listing 6.2. This one has a wide variety of types embedded in its variants. So our enum is called message. We've got 4 variants: quit, move, write, and change color. And they have different types. Quit has no data associated with it at all. Move includes an anonymous struct inside it. Yes, brackets. Braces. Curly braces. Curly brackets or braces. They've given us some white space here and here. Okay. But no struct name, because it's an anonymous struct. And the word struct doesn't appear either. And I guess this means that they don't define this struct anywhere. So it's just like a tuple, but with named fields, which I guess is what a struct is anyway. Write includes a single string, and change color includes 3 I32 values. And I'm assuming this is a tuple of I32 values, of 3 of them. Defining an enum with variants such as the ones in listing 6.2 is similar to defining different kinds of struct definitions, except the enum doesn't use the struct keyword, and all the variants are grouped together under the message type. The following structs could hold the same data that the preceding enum variants hold. Okay, so you could have a struct called quit message, and they're saying it's a unit struct because it doesn't have any data associated with it, and we learned about how unit structs, words from the previous chapter that I'm not going to go back to. But we can see here that a unit struct is a struct that is a data type, but it doesn't seem to have any fields at all. All they care about is naming the data type. Okay, and then we can have a struct that they've named move message, and okay, it's just a regular old struct because now there is the struct keyword and move message is the name of it, and we have our scope braces and the fields with names and types. Now we have struct write message give me a string, which is a tuple struct. Would you look at that? So I was curious if you have, see, this is how bad my eyes are at bringing in data and then me remembering it, right? It's like my vision is fine and my brain's fine. It's not the fastest, but it does the job. But it's like I don't have a connection between my eyeballs and my brain, or it's like a dial-up connection or something. Because I even, transferred this. So we have a tuple struct, and a tuple struct takes this same syntax as it looks like what enum variants take. So there's a name, and then tied up against it, comfy, snuggled up, or open parentheses. It looks like for a parameter, or for this, yeah. So this is a place to put your parameter, and then if we're instantiating one, that'll be a place to put the argument. So it really is the same thing as this, and so that makes me want to say this really is an empty tuple. This is also a tuple struct, the I32s. Yes, okay. But so yeah, this is a tuple struct, which means I want to say that this is a tuple, and the contents of the tuple is one single instance of a string. Yes, this is consistent. I'm okay with it. Moving on. But if we used the different structs, which each have their own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6.2, which is a single type. Right. So if we wanted a function that would willingly accept quit message, move message, write message, or change color message, we would have to put that in the function's parameters. And I guess we haven't. Earlier in the book, they didn't introduce it. They just used it. The ampersand as the and operator. So I'm thinking that we would use something like this. Is this maybe the or operator? In the struct definition, in the function definition. Okay, there's one more similarity between enum and structs. Just as we're able to define methods on structs using an implementation block, we are also able to define methods on enums. Here's a method named call that we could define on our message enum. So an implementation block, we implement message. So then we have a function call, and it takes a reference to self, and then there would be a method body, right? We didn't feel like writing this part. And then let m, so message example, let m equal a message, right? And then I'm getting tired. So read words and listen to them later. Sir, yes, sir. The body of the method would use self to get the value that we called the method on. In this example, we've created a variable m that has the value message write string from hello. And that is what self will be in the body of the call method when mcall runs. Okay, so it's an implementation. Got it. Let's look at it's a method. Yes, it's an implemented method. Let's look at another enum in the standard library that is very common and useful, option. The option enum and its advantages over null values. In the previous section, we looked at how the IP-adder enum lets us use Rust's typed system to encode more information than just the data into our program. This section explores a case study of option, which is another enum defined by the standard library. The option type is used in many places because it encodes the very common scenario in which a value could be something or it could be nothing. Expressing this concept in terms of the type system means the compiler can check whether you've handled all the cases you should be handling. This functionality can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, null or not null. In his 2009 presentation, Null References the $1 Billion Mistake, Tony Hoare, how are you? Has this to say, I call it my $1 billion mistake. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. The problem with null values is that if you try to use a null value as a not null value, you will get an error of some kind. Because this null or not null property is pervasive, it's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. And the problem isn't really with the concept, but with the particular implementation. Rust doesn't have nulls, but it does have an enum that can encode the concept of a value being present or absent. This enum is option, and it's defined by the standard library as follows. Enum option t. So what do we call this? Pointy bracket. Okay. So wait. So t here. This is. I'm not being serious now. T. So option is less than t and greater than this brace. Option less than t greater than. So t is greater than the option. I'm not being serious. I'm trying to come up with what I want to call this. So greater than option, less than body. Less than the fields, less than body. Oh, they're not fields because this is an enum. Less than the variance. So bump. Yes, because it's greater than this, and then it comes back down, and that wait, no. It's less, so option is less than t, and so t is bigger than option, and then it gets smaller again and goes back down. So I'm going to call this a t bump, and I probably am not really. The option the option t bump enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. In addition are its variants. You can use some and none directly without the option prefix. The option t-bump enum is still just a regular enum, and some t and none are still variants of type option t-bump. The t-bump syntax is a feature of Rust we haven't talked about yet. Well, I have. It's a generic type parameter, and we'll cover generics in more detail in Chapter 10. For now, all you need to know is that t-bump means the sum variant of the option enum can hold one piece of data of any type. Here are some examples of using option values to hold number types and string types. We can say, so here's my enum option generic type. So, alright. The option, so this is not a parameter exactly, because the parameter is down here. This is where the tuple is that contains a generic type, but then tacked onto the side of the option is the, I switched to using Atom because I just wanted to. I'm starting to feel dirty using Microsoft VS Code. But then again, here we go. Yes, I'm one of those people. Function so useful. Let some number, oh, go away. Let some number equal sum 5. And let some string equal sum a string. Let absent number equal option I32 hold on. Let absent number, which is an option I32, equal none. Let x, which is an I8, equal 5. And now we want to say let y, which is an option I8, equal sum 5. Let sum sum equal x plus y, and it doesn't work, and they will explain. If we use none rather than some, we need to tell Rust what type of option t-bump we have, because the compiler can't infer the type that some, you know, it'd be funny is if I acted like I was confused about infer and imply, and then just said imply every time I see infer for the rest of the book. I should read it as imply, and see if I can get someone to make a comment about it. Okay, here we go. If we use none rather than some, we need to tell Rust what type of option t-bump we have, because the compiler can't imply the type that the sum variant will hold by looking only at a none value. Okay? Oh yeah, the compiler can't imply... That's harder for me to understand when I say the wrong word. The compiler can't imply the type, can't infer the type that the sum variant will hold by looking only at a none value. And that matters. When we have a sum value, we know that a value is present and the value is held within the sum. When we have a none value, in some sense, it means the same thing as null. We don't have a valid value, so why is having option t-bump any better than having null? In short, it's because option t-bump and generic t, where t can be any type, are different types. The compiler won't let us use an option t-bump value as if it were definitely a valid value. So, for instance, this code won't compile because it's trying to add an I8 to an option I8. So this is an I8, and this is optionally an I8. We had the option of making it be a whole lot of nothing. If we run this code, we get an error message like this. Let sum sum equal x plus y, but no implementation for I8 plus standard option I8. Intense. Camping is intense. In effect, this error message infers that Rust doesn't imply how to add an I8 and an option I8 because they're different types. And that's why we did it. We did it on purpose. Right, because you might have you want someone to return, you want the user to return something into standard input, and they might not. Maybe what they return is parsed out. You know, it's not going to work. So you just say, okay, well, there's nothing in there that we're going to save, but then they've given us something, and so that is a result, and so we have to. I mean, I can envision other ways of getting around it. Like you could have you could enumerate the types of input, or the types, anyway, so so what's going on here is not, oh man, we have to figure out how to work around this. No, we don't want to work around this. That's what this is for. Because this might be none. That's why we made it an option, because we're saying, okay, hold on now, this might come out as a whole lot of nothing, in which case we don't want to be trying to add it here. So they're going to tell us how to unpack the I8 out of option I8. I don't think they're going to tell us how to, say, implement adding, addition, summing, addition, implement. Yeah, they're not gonna, I don't think they're gonna hold our hand and show us how to undo the work we did by making options. I don't know, I felt like I had something there, but it is now permanent on the internet. Where was I? How long have I gone? 40 minutes, that's about right for me. Right, so what it really says, okay, so the error message means Rust doesn't understand how to add an I8 and an option I8 because they are different types, and we did that on purpose. When we have a value of a type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever type of value we're working with, only then do we have to worry about possibly not having a value, and the compiler will make sure we handle that case before using the value. In other words, you have to convert an option bump t to a t before you can perform t operations with it. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it is. Not having to worry about incorrectly assuming a not null value helps you to be more confident in your code. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value option t-bump. Then, when you use that value, you are required to explicitly handle the case when the value is null. Everywhere that a value has a type that isn't an option t-bump, you can safely assume the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. So, how do you get the t value out of a sum variant when you have a value of type option t-bump, so you can use that value? The option t-bump enum has a large number of methods that are useful in a variety of situations. You can check them out in its documentation. Becoming familiar with the methods on option t will be extremely useful in your journey with Rust. In general, in order to use an option value, you want to have code that will handle each variant. You want some code that will run only when you have a sum t value, and this code is allowed to use the inner t. You want some other code to run if you have a none value, and that code doesn't have a t value available. The match expression is a control flow construct that does just this when used with the enums. It will run different code depending on which variant of the enum it has. And that code can use the data inside the matching value.